In this lesson, we're going to go into depth on measurements. Now, in order to talk about measurements, we need to know how to round numbers. We also need to know how to round numbers with significant digits. We need to also be able to tell the difference between a couple different kinds of errors and how to calculate those errors. Now, significant digits, for some of you who may have seen this before, this will be a nice review. For those of you who have not seen significant digits before, I would take careful notes because there's a lot of rules with these. And to understand why significant digits are important, let me give you a little scenario. Imagine you go to the doctor's office and you get weighed on a scale, and the scale says you weigh 150 pounds. The doctor records it as 150.00. And then somebody else goes to read your chart. This is going to be misleading because by the doctor writing down 150.00 rather than 150, what happens is it incorrectly implies that you know the weight to the nearest hundredth of a pound. And we only measured it to 150, which is a whole number. By putting that 0.00, whoever is reading it will think that it was measured to 100th of a pound. So the decimal places are really important in conveying a message to whoever is reading it on how it was measured. So now, let's go through and talk about what makes a digit significant. Well, first of all, let me stress to you that a significant digit represents an actual measurement. Let's go through the rules here. Any non-zero digit is always going to be significant. So in this example here, 4, 5, 6, all three of those digits are significant. So we would say that that number has 3 significant digits. 3, 5 has all non-zero digits. So both the 3 and the 5 are considered significant and they represent some measurement. So in that example, 35 has 2 significant digits. The tricky part with the significant digit rules comes into play when you're trying to decide whether or not a 0 is significant or not. Now keep in mind what we call trailing zeros, and I'll make a note of that here. This is called trailing zeros. If you have a 0 that follows a non-zero digit to the right of the decimal place, that's called a trailing 0. And those are going to be considered significant because it helps us determine to what decimal place we measured. So instead of writing 4.2, if we write 4.20, that tells us that we measured to the hundredths place, which is the second decimal place. If I just wrote 4.2, that tells me that I only measured to the tenths place. By putting that trailing 0 at the end, I know that I actually measured out until the hundredths place. So any trailing zeros is going to be considered significant. So this 4.20 number has 3 significant digits. In this case, the 0 is included as a significant digit. In this next example here, 8.00. Those 2 zeros are trailing zeros because they come after a non-zero digit to the right of the decimal place. Because this is written as 8.00, I know again that this was measured to the nearest hundredth. Rather than if I just wrote 8, 8 would mean that I just rounded to the nearest whole number. By putting that 0.00 in there, we're being a lot more accurate and letting the reader know that we actually measured to the nearest hundredth. Okay, the next rule says zeros between non-zero digits or other significant digits are always significant. So when you have a 0 that lies between 2 significant digits, whether they're non-zero or whether they're 0, if you have a 0 that lies between 2 significant digits, those are going to be considered significant. So when we look at this first example here, 4002, These two zeros here that I just underlined are between two significant digits, the 4 and the 2. The 4 and the 2 are significant because they're non-zero. And then the two zeros in between are significant because they're between two significant digits. So in all, the 4002 has 4 significant digits. Same thing with this one here, the 3.06. That 0 falls between two significant digits. The 3 and the 6 are non-zero, so those are considered significant digits, and because the 0 falls between them, the 0 is also considered significant. So in the case of 3.06, there are 3 significant figures, the 3, the 0, and the 6. In the next example, 30.0. The 0 in the center that's in bold is considered significant because it is between two significant digits. Whether they're 0 significant digits or non-zero significant digits, it's between two significant digits. The 3 is definitely significant because it's non-zero. The 0 to the right of the decimal place is considered significant because it is a trailing 0. It's a 0 that comes after the decimal place, and it's to the right of all the non-zero digits. So this digit that I'm highlighting, let's do green. This digit right here is a trailing 0, so that's significant. This is a non-zero number, so that's significant. And then the 0 between two significant digits is also considered significant. So in the case of 30.0, we have 3 significant figures. In the next rule, we have zeros to the left of the first non-zero digit. Those are never significant because those zeros do not represent a measurement. So let me underline this maybe, and let's do blue. These zeros right here that I just underlined in blue are not significant because it's to the left of a non-zero number, and it's the first non-zero digit. That 6 is the first non-zero digit. So anything to the left of that, if it's a 0, does not count. Those zeros do not fall between two significant digits. So the only significant digit in the case of 0.006 is the 6. Same thing with this. The 5 is the first non-zero digit. Anything before that, if it's a 0, is considered not significant. Now, if there was, I'm just going to add something in, but don't write it in your notes because this isn't part of the example. I'm just doing a what if. If this was a 70.00052, then all those zeros would be between the 7 and the 5, and they would count as significant because they fall between two significant digits. However, because there isn't a non-zero digit to the left of all those zeros, all of those zeros leading up to the 5 are not significant. So the only significant digits in 0.00052 is the 5 and the 2. The last rule, if you have zeros to the right of the last non-zero digit, but on the left-hand side of the decimal point, they are not considered significant unless otherwise stated. So you can always assume if you have, say, 30,000 or 75,000, that all those zeros are insignificant unless otherwise stated. So all of these zeros here, they do not lie between two significant digits, and they're on the left-hand side of the decimal place. So they are not considered significant. None of those zeros represent a measurement. And the same thing with this. This 0 here does not count because it's to the left of the decimal place and to the left of significant digits. It's not between two significant digits. So the only significant figures in the 2 and the 1 and the 0 is the 2 and the 1. Unless, of course, it's otherwise stated. Okay, let's do some examples here that are not already done out so we can practice, and we'll state what the meaning is. We have a time measurement of 11.90 seconds. In this case, we have 4 significant digits. Non-zero digits are always significant. So the 1, and the 9 are definitely significant. The tricky part comes when you're trying to decide if the 0 is significant or insignificant. This 0 right here is what we call a trailing 0. It's a 0 to the right of the decimal place, and it's also to the right of the last non-zero digit. So this is considered a trailing 0, which means it is considered significant. And what it tells us is, instead of writing it as 11.9, we write it as 11.90 because whoever took that measurement wants to convey the message that it was measured to the nearest hundredth. Okay, in the second example, we have a length that's measured in meters. We have 0.000067. When we look at those zeros, we have these zeros, and we have this 0 here, but they are not between 2 significant digits. The 6 and the 7 are for sure significant because they're non-zero. Those other zeros are not between 2 significant digits. This is definitely not a significant digit, which makes these not significant. So in this case, we only have 2 significant digits. And this tells us that it was rounded to the nearest 6 decimal place. So measured to the nearest 6 decimal places. Okay, the next example, a weight is measured in grams. And the same thing as the previous examples, unless stated otherwise, these zeros here that I'm underlining in pink are not significant because they do not fall between 2 significant digits. The 3 is definitely significant. The 0 to the right of the 3 is significant because that is a trailing 0. It is a 0 to the right of a non-zero digit, and it's on the right-hand side of the decimal place. So that's considered a trailing 0. So in this case, we have the 3 and the 0, which are significant. So we have 2 significant digits, and this tells us that it was measured to the nearest 4 decimal places. Measured with 4 decimal places. Okay, the last example says a population reported as 240,000 people. Now, these zeros, the 2 and the 4, are definitely significant. These zeros are not significant because they do not fall between 2 significant numbers. And they're not trailing zeros because they're not to the right of a decimal place. So the only significant digits we have here are the 2 and the 4. And this tells us that it was rounded to the nearest 10,000th place. If we look, these two are significant, and if we count over, here's 1, tens, hundreds, thousands, and then 10,000ths. So this tells me it was measured to the nearest 10,000th place. So the biggest thing with the significant digits is understanding the rules with the zeros. The zeros can be a little bit tricky, but just remember, in order for a 0 to be considered significant, there needs to be one of 3 things. It has to be specifically stated in the problem, or it's got to be a trailing zero, or it's got to be between two significant digits. Those are the three ways that a zero can be considered significant. Okay, the next thing we're going to talk about is just rounding rules in general. So for a moment, put your understanding and the rules that we just went over for significant digits, just put that aside for a second. And let's think back to grade school, middle school, high school, when we had to do some arithmetic and we were told to round it to a certain number of decimal places. So just a quick review in case you haven't done this in a while and you forget. I have the decimal place value chart up here in the notes. Okay, so your decimal goes here. Notice anything to the right of the decimal is going to end in THS. So anything to the left of the decimal does not have that TH on the end of it. It's just ones, tens, hundreds. But if I wanted to make sure that I'm telling the reader that I want to go to the right of the decimal place, I would add that THS on the end. So instead of saying round to the tens, I would say round to the tenths with a TH on the end if I want to go to the right of the decimal. Now the general rounding rules, just again, if you need a refresher, if someone says to round to the nearest whatever decimal place, you first want to decide what is the smallest decimal place that should be kept, and that's what is asked of you in the problem. Okay, once you identify that in the number, then you want to look at the number to the right of that place, and if it's a 5 or bigger, you want to round that digit that you want to keep up. If it's a 4 or less, you want to keep it the same. Okay, so let's go through a couple of examples just to refresh. Okay, so we want to take 382.2593 and round it to the nearest hundredth. Because of that TH, I know that means I want two places after the decimal, right? So here's my hundredths. If I'm looking at it in my chart, that's two places after the decimal. So I want 382.2 and then some number. Now, to decide if I need to change that 5 that comes after the 2 to a 6 or keep it at a 5, I need to look to the number to the right of the 5. Since the number to the right of the 5 is a 9, and that's bigger than 5, I'm going to round up to a 6. So 382.2593 rounded to the nearest hundredth would be 382.26. Now if I take that same number, 382.2593, and I want to round it to the nearest tenth, that's one place to the right of the decimal, tenth, that has that TH on the end of it, so I know it's going to be to the right of the decimal. So I want to have 382 point and then one decimal place. So do I keep it a 2 or do I bump it up to a 3? We only can tell what to do if we look at the decimal place to the right of what we want to keep and decide if it's 5 or bigger or 4 or less. Since the 2 has a 5 to the right of it, that 5 tells me that I need to bump the 2 up to a 3. So the answer is going to be 382.3. Now I want to take 382.2593 and round it to the nearest 1. That means there's going to be no decimal place. If we look up here, we want everything up to here and then stop at the decimal. We don't want anything to the right of the decimal. So I want to keep 3.8, but I got to figure out if that 2 needs to be bumped up to a 3 or not. Since this 2 is 4 or less, then I'm going to keep it as 382. Now that's rounded to the nearest ones. Another way that could be stated is to the nearest integer or the nearest whole number. Okay, the next example, 382.2593 needs to be rounded to the nearest 10. That's 2 places to the left of the decimal. Here's my tens place. So I don't want to keep any of the digits after that 8. I want 380. I look at this 2 to see if it's 5 or bigger, to see if I need to bump up that 8 to a 9. If I have 382 and I want to round it to the nearest 10, is 82 closer to 80 or is it closer to 90? That 82 is definitely closer to 80, so I'm going to keep 380. And then here's my tens place. Okay, round it to the nearest 100. So I just want to keep this digit and get rid of everything else. The 382.2593, I want to look at the number to the right of the 100 place. That's an 8, so that means I need to bump the 3 up to a 4. 382 is closer to 400 than it is to 300. I want to round it to the nearest 100, so I got to round it to 300 or 400. That 382 is definitely closer to 400 because that 8 is over 5. It's 5 or bigger. So I'm going to round it to 400. Now, when we're going to put these two together, rounding with significant digits, in this example, it gives you some operations. And then it tells you how to round it. Do you want to round it to so many significant digits? So, in the first example, it says we're going to take 7.7 and multiply it by 9.92. When we do that on the calculator, we take 7.7 times 9.92, we're going to get 76.384. That is the correct answer. However, we need to approximate it and round it to 2 significant digits. So, in order to do that, I have to just write it as 76. So I have 2 significant digits, the 7 and the 6. In the next example, we're going to take 240,000 and multiply it by 72,106. That's a really big number, and when I put that in on my calculator, it's giving it to me in scientific notation. So that would be 1.730544 times 10 to the power of 10. That is the answer. That is the correct answer. But then, in order to approximate it, to give our final answer, we're going to approximate it with 4 significant digits. I only want to see either 4 non-zero numbers or numbers with zeros in them that are considered significant. So, if I look at this here, I have 1, 2, 3, 4. Because this 5, that number is 5 or bigger, I need to round this 0 up to a 1. So I'm going to write down 1.731 times 10 to the 10. Now I have this written with 4 significant digits. 1731. If you've never done this before with significant digits, I really recommend that you write these rules down on like a cheat sheet for yourself. So while you're working on your homework, you have them available. Once you use them enough time and you look at your cheat sheet enough times, you're going to start to remember these rules. But you need to have that sheet in front of you to keep referring back and forth to it until you get comfortable with it. Okay, now we're going to talk about how to recognize different types of errors. And generally speaking, measurement errors usually fall into 2 categories. You either have random errors or you could have systematic errors. Now, to help you understand the difference between the two, a random error occurs because of an unpredictable event that you don't really have control over when you're doing that measurement process, okay? And a systematic error occurs when that problem in the measurement affects all of your measurements. So, for example, let's say you go into a pediatric office with your child. You have a new baby and you want to get the baby measured. And the baby is put on that little scale, is laid down, and the baby's not happy, and the baby's crying and thrashing its legs around and wants to be picked up by its mama. And because of all that jiggling around that baby's doing, it's gonna throw the measurement off. So maybe instead of weighing 14.5 pounds, you end up measuring 15 or 15.5 pounds or something like that because the baby's moving around so much. That is a random error. It's unpredictable and it's hard to control. So that would be considered a random error. But now a systematic error might be an example of, let's say you work in the pediatrician office and all day you've been measuring babies. Okay? At the end of the day, you notice that the scale was not zeroed out at the beginning of the day and it was off by a half a pound. So every single measurement that you took during the day, every baby that you weighed on that scale is going to be off by a half a pound. That's a systematic error because it affects every single measurement. Okay? So now that you have an idea of the difference between random errors and systematic errors, let's go through another example that I have here in the notes. We have an example of a random error where you have temperatures that are measured with a simple thermometer and the data was recorded by hand. Some of you that are old enough remember the thermometers that had the mercury in it, and your mom always told you, be careful, don't bite down when you're taking your temperature. You don't want to accidentally break the glass thermometer and get that mercury in your mouth. So those thermometers were very hard to read and were very old-fashioned, very simple, not high-tech, not digital. It was very hard to read those. So it was because of the measurement tool, and maybe if you were writing it down by hand, maybe if the person had sloppy handwriting or read it off the thermometer wrong and wrote it down wrong, or just did just was thinking, that the temperature was 98.5, but accidentally wrote down 98.3. Those are random errors. A systematic error is when it affects every single measurement. So the example that I have here in the notes is if you want to make an average estimate of a country's temperature, and these scientists go out and only measure temperatures in the city, they're systematically going to be higher, all of those temperatures, because in the city you're going to have more body heat, you're going to have more activity, and all that stuff that's going to create the temperature in the city to go higher, versus if they did, measurements in the cities and in the rural areas and averaged them together, it would be a better measurement. But if someone is only measuring temperatures in the city, that average temperature is going to be systematically higher. Okay, now talking about how to calculate error, we have two kinds of errors that we can calculate. We have the absolute error and we have the relative error. If you think back into one of our previous sections, we talked about absolute change and we talked about relative change. This is basically the same idea, but we're applying it to errors. The absolute error is the difference between the measurement and the true value, and the relative error is the change, the percent change from the measurement to the true value. So it's basically the same calculation we did before. So if we were to write down the formula for this, the absolute error, that's going to be the measurement minus the true value. The relative error is the amount of error in terms of a percent. So we're going to do the measurement minus the true value. We're going to divide by the true value. and then multiply it by 100 to change it to percent form. In example A and example B, we're going to find the absolute error and the relative error. So, example A says your true weight is 125 pounds, but a scale says you weigh 130 pounds. So when you're looking for the absolute error, you're going to take your measured weight, in this case, which is 130 pounds, and you're going to subtract your true weight, which is 125 pounds, and you're going to get an error of 5 pounds. There's a 5-pound difference error. Okay, now if we were to do this to figure out what it was in terms of percent, we're going to take the measured value minus the true value, divide by the true value, and then multiply by 100 to put it in terms of percent. So when we put that in on the calculator, and keep in mind, when you put that in the calculator, you have to put parentheses around the numerator so that the calculator knows that 130 minus 125 is all in the numerator. When we do that and then we multiply by 100%, we're going to get a 4% error. Okay, the next example says the government claims that a program costs $49 billion, but an audit shows that the true cost is $50 billion. So to find the absolute error, we're going to take the measured amount and minus the true amount. So the measured amount is what they claim, which would be the 49 billion. We're going to subtract the 50 billion, which is the true amount, and that means we're down $1 billion. Okay, now to find the relative error, we're going to take the measured amount minus the true amount, divided by the true amount, and then multiply by 100 to change it to percent form. And when we do that, that means we're going to be down by 2%. We've estimated too low of an amount by 2%. Okay, in the last part of the lesson, we're going to talk about accuracy and precision, and then we are going to combine it in with significant figures and rounding rules. Now, with accuracy, that tells us how close we are to the true value. The closer we are to the true value, the more accurate we are. The precision tells us how detailed we are. The more detail in the measurement means the more precise we are with our measurement. So an example that it might help clarify the difference between the two, this example I have in the notes, it says, suppose your true weight is 102.4 pounds. The scale at the doctor's office can only be read to the nearest quarter of a pound, meaning it can only be read with 0, 0.25, 0.75, and then up to the next integer. So it can only be read in quarters, okay? Then when you get on the scale of the doctor's office, it says you weigh 102.25 pounds. Now that's really close. The 102.4 is your true value, and the doctor's office is saying you weigh 102.25 pounds. So that's really close to your true value. Then when you go to the gym, it gives you a digital readout, and the gym's digital scale weighs you to the nearest 0.1 pound, or a tenth of a pound, and it says you weigh 100.7 pounds. Which scale is more precise and which scale is more accurate? Remember, accuracy tells us how close we are to the true value. So if we look, this is your true weight. Let's write this down, 102.4. That is your true weight. Then 102.25 is the scale at the doctor's office. And then 100.7 is the scale at the gym. If you notice, the difference between the scale at the doctor's office and your true weight is a lot smaller than the difference between the gym scale and your true weight. So the doctor's office scale is much more accurate because it's much closer to your true weight. So the doctor's office scale is more accurate. And again, that is because the doctor's office scale is reading your weight at a much closer value to your true weight versus the gym's. Now, the gym's scale is actually going to be more precise because it can weigh with a lot more detail. The scale at the gym can read every 1/10 of a pound. It can read when your decimal place is exactly 0, like if you're exactly 150 pounds, it would read it as 150.0. Then it can read it at 150.1, 0.2, 0.3, 0.4, 0.5, etc., all the way up to 151. So there's a lot more detail there, whereas the scale at the doctor's office can only read you at 150.0, 150.25, 150.5, and 150.75. It can only read based on the quarters, where the gym scale can read you a 1/10 of a pound. So the gym scale is much more detailed. So that means the gym scale is more precise. Okay, now when we combined precision and accuracy with significant digits and rounding, there are some rules. Whenever you're doing operations with measurements, or sometimes we call them approximate numbers, if you're multiplying and dividing, you want to make sure you're using accuracy. So when you're multiplying and dividing two numbers, what you want to do is look for the number that has the fewest significant digits. When you're dealing with accuracy and how close you are to the true value, that's going to affect your significant digits. So multiplying and dividing, we're going to look at the number with the smallest number of significant digits, and that is how we are going to round our final answer. So if we look at this example down here, example B, we're going to apply multiplication and division rule to this. It says the government in a town of 82,000 people plans to spend $41.5 million this year. Assuming that this money is going to come from taxes, what is the amount that they need to collect from each resident? So they need $41.5 million for a budget in this town, and the town has 82,000 people, so we need to divide that budget to see how to tax each person. So we're going to take 41.5 million, which is 415 with 5 zeros. That's 41,500,000. And we're going to divide that amount of money with 82,000 people. Now, remember, with multiplication and division, we want to look at and use accuracy. And with accuracy, we're looking at the number of significant digits. We want to take the number with the fewest significant digits. This number up here has 3 significant digits. This number down here has 2 significant digits. So when we write out our answer and we round it at the end, we want to make sure that we use the lower number of the significant digits. So we're going to round it to 2 significant digits. Okay, so if I take 415,000,000 and divide by 82,000, That's going to give me an answer of 506.097561. But we need to approximate it using two significant digits because this is the smaller of the two. So if I need to round 506.097561 to two significant digits, the only way that I can do that is if I round it to $510. So as an approximation, I can say that there's $510 in taxes for each person in this town so that the town has enough money in the budget to run its day-to-day functions. Okay, now, going back, that's multiplication and division. When you're doing multiplication and division, you use the smallest of the significant digits. When you're doing addition and subtraction, you want to use the least precise number. So you're going to look at how the number is rounded in the problem. So that would be example A here when we use addition and subtraction. It says a book written in 1985 states that the oldest Mayan ruins are 2,000 years old. How old are they now? So this is year 2020. So from 1985 to 2020, that's 35 years. So back in 1985, they approximated the oldest Mayan ruins at 2,000. So we have to add on 35 years to that. So we're going to take 2,000 and add 35 years. When I do that, I get 2,035 years. However, when we round it to our final answer, using our rules for accuracy and precision, since I'm adding, I want to look for the least precise number. That means the number with the least amount of detail. This number here has the least amount in detail because it's rounded to the thousands, whereas this is rounded to the ones. So the 2,000 has the least amount of details in the number. It's the least precise. So I want to make sure that when I round my answer, I'm going to round it to the same place as 2,000. And to change 2,035 to have the same place, I want to round it to the thousandths, I would have to write my final answer as 2,000 because 2,035 is not close enough for me to be able to bump it up to 3,000. Because we have to round it to the thousands, because this is the least precise number, we either want to keep it at 2,000 or bump it up to 3,000. And 2,035 is definitely not past 2,500 where we can bump it up to 3,000. So we have to keep it at 2,000 years as an estimate. So, quickly to sum up, when you're using your accuracy and precision rules, when you're multiplying and dividing, you want to use the fewest number of significant digits. When you're adding and subtracting, you want to look and use the placeholder of the least precise number.